Welcome back. This is the second lecture on mirror descent. We're going to be getting a little bit more into the specifics. So let's take again as our starting point the subgradient method. And let's remember our guarantees for this. So minimizing a function f of x that's convex, subject to convex constraint. For a lot of this, I'm leaving out the dependence on the convex constraint. As we saw when we talked about subgradient descent, projection basically comes for free in terms of rates, but it comes at the expense of extra writing and extra notation. So I've been kind of leaving it aside for now. Everything carries over really without change. So leaving this aside for now, remember that subgradient method tells us that we should choose xt plus 1 equals xt minus eta times gt, where gt is an element of the subdifferential of f at xt. And this is equivalent to minimizing this linear approximation plus a proximity term. xt plus 1 is equal to the argument of eta times gt x plus 1/2 times x minus xt. And what we've seen is that if we take step size eta, that's equal to some bound at least on how far we are initially, there can be an upper bound on this, divided by L and square root of t, where t is the total number of steps we wish to take, and L is the Lipschitz constant for f. Then, after t steps, suboptimality is controlled as follows. F of 1 over t times the sum of xt, this is the trajectory that we generate, t equals 1 to capital T minus f of x star is bounded by how far I initially start times L divided by square root of t. And so far, we have mostly been focusing on this, most of the focus of this class. But now it's time to turn to L a little more carefully, a little more closely at L. And let's do this through a specific example of robust regression. Typically, in ordinary least squares, we try to minimize ax minus b squared. But as we've talked about and has been observed in many settings, squared loss can be very susceptible to outliers. Very sensitive to outliers. So instead, what we could try is the L1 loss. So we could try to minimize ax minus b, the L1 loss. So let's see what this does for us. So again, this is also convex. So let's try to understand how we could apply subgradient method to this. It certainly applies because it's convex, and we note that we probably can't implement gradient descent because this is not a smooth function. Because it's L1, it has these absolute values, which is going to have these points. And so we can do subgradient method. Maybe there are other more fancy things, but for the point of this discussion, let's just consider that. So thinking back to the previous slide, we need to figure out what the Lipschitz constant is. So we need to know what's the Lipschitz constant L for our function f, which is again now equal to ax minus b, the L1 norm. So again, remember what this means is I need to understand the absolute value of f evaluated at x, that's ax minus b, minus f evaluated at y, that's ay minus b. And I need to somehow upper bound that by L, which is the constant I'm after, I want to compute that, times x minus y. Let's do a little bit simpler version of this calculation. So to simplify the calculation, it still gets the main point. Let's just set A equal to the identity and B equals 0. So in other words, let's just do the simpler task of computing the Lipschitz constant of the function f of x equals the L1 norm of x. Just a little bit easier. Okay, so what do we have? We've got the L1 norm of x minus L1 norm of y. I want to upper bound that by L times x minus y. Well, we can see that, let's do this at a particular point. So let's take x equal to the all ones, 1, 1, which I'll denote by this bold-faced 1. And let's let y be something that is a little bit bigger, so it'll be 1 plus epsilon in every coordinate. So it will be 1 plus epsilon, 1 plus epsilon. Or in other words, just 1 plus epsilon times this all ones vector. So what do we have here on the left and the right? Well, the L1 norm of x is just the sum of all of these. So I've got n minus 1 plus epsilon times n. The absolute value of that is equal to epsilon times n. And I need to upper bound that by L times the 2 norm of x minus y. Now what is, let's do this computation here on the side. What is this? So the 2 norm of x minus y, this is equal to, x minus y are easy to subtract. X is the all ones vector, y is the all 1 plus epsilon vector, so their difference is just going to be minus epsilon times the all ones. This is equal to the square root of the sum of epsilon squared, which is equal to epsilon times the square root of n. Okay, so plugging this in here, I've got that epsilon n is less than or equal to L times epsilon times the square root of n. Now, we need to choose L in order to make this upper bound true. And the only way to do that is to take L bigger than square root of n. So I need to choose L equal to the square root of n, which is a very large number. In particular, it's dimension dependent. The dimension here is n. I have n variables, and I need my Lipschitz constant to be square root of n. So this is the key point here. So in this example, this is dimension dependent. Why is this so important? I don't like flipping back too much, but I'm going to do it just so I don't have to repeat what I had written. So if you look back to the first slide here, we see that our upper bound is L over square root of t. And we talked about how this is, in general, we like to think about this as dimension independent. But now our L is actually going to be equal to square root of the dimension. So that means that if I double the dimension, then the amount of iterations I need is going to increase. So what we see is that this example shows that our previous guarantee for the subgradient method, which was x1 minus x star times L over square root of t, this is our convergence guarantee for subgradient method. May be hiding dimension-dependent constants. As it is in this example. So let's see exactly a little bit more generally what was happening in the previous example of robust regression. If we have a function that minimize f of x, again, subject to x in x, I've been kind of ignoring for the reasons I've stated. The set constraint, it really doesn't make too much of a difference so far. And let's suppose that it is Lipschitz. So let's suppose it is Lipschitz, but with respect to a different norm. Suppose it is one Lipschitz but with respect to a different norm. As an example, which is very close to the example that we saw, suppose that the gradient of f of x in the infinity norm is bounded by 1. Remember that an upper bound of the gradient is exactly the same as Lipschitzness of the function. So just to make this clear, remember that we have exactly this for the L1 norm, which we considered. Because the L1 norm, if you think about what its gradient is going to be, it's just going to the gradient of any point that's not at that point, which isn't equal to 0, which isn't at the point of the bottom of the V, is going to be either +1 or -1. So every single entry is +1 or -1, which means that the largest absolute value of any entry is at least 1, which is exactly what we have here. So suppose we have this nice property. We know that in this infinity norm, the gradient is always upper bounded by 1. The problem is that we can't use this with our current technology. So our current bounds only work with L as computed using Euclidean norm. So that means that if I tell you this thing about f, you have no choice but to convert that into a Lipschitz guarantee in the L2 norm. And the best that we can do is to incur this square root of n. So without any further information, the only thing we can say about this, about the infinity norm of the gradient of f of x being bounded by 1, is that the 2 norm is bounded by square root of n. And that's exactly what we saw in the specific example of robust regression. And therefore, we have to incur this square root of n. Mirror descent wants to fix this. And it wants to fix this by changing the geometry. And the idea is to set xt plus 1 equal to, again, a linear approximation, gt, oops, it's the argument of this, eta gt transpose x plus 1/2 x minus xt. We're going to change this the same way that we proposed changing it in that very first example we did in the previous lecture. We saw that we rescaled space and we got an algorithm that moves directly towards the minimizer. So we're going to pick this up in the next lecture, give the specific guarantees, the specific algorithms and definition we need in order to define mirror descent and see how well it works. We'll pick it up next time.